is we're still confused. So these results hold regardless of the state space being finite or infinite. So the result below hold regardless of S being finite or infinite. Alright? So there's not really change the statement if I have an infinite state space. So the thing is, however, if the state space has a finite, then pretty much I can say a lot about the limiting behavior. So if S is finite, right? Let me recall the decomposition of S. Namely, S can be written as T union with R1, union with RK, right? Where T is a transient and the R, so say where T, the transient state. T is that collection. Ri is what the closed set, irreducible, of what do you say? Closed, irreducible, consisting of recurrent states. Right. So I should say Ri is closed, finite, I guess, is a closed finite. Alright. So if you think about, let me say, each of the Ri, they are a state space itself. So here, the say Ri can be considered as a state space, for the Markov chain itself, for itself. This is because if I start in the Ri, I cannot get out. So that I can consider Ri being a state space of its own. Right? So now, given the fact that Ri being finite, irreducible, and recurrent, right? So now, Ri being what? Being irreducible, right? So being irreducible plus being recurrent, right? So according to the last line above there, I'm gonna have a stationary measure mu on Ri. But because Ri is finite, I can just normalize it to be a stationary distribution. So Ri being this line, that this a stationary measure, say mu I, concentrated on Ri. In other words, for all, say Z not in Ri, mu I Z is is finite. Mu I can be normalized as a what? Mu I can be normalized as a stationary distribution. Stationary distribution pi I concentrated in Ri. In other words, I have pi I of x. So say mu y is mu I y divided by summation for the z in Ri mu I of so that says basically what you have. Suppose my S here can be decomposed into this collection. Then say on R1, I'm gonna have a stationary distribution concentrated in R1. Similarly, all the way up to this Rk here, I have another stationary distribution, pi sub k concentrated in Rk. So I should say, in other words, I have what? Summation of pi I z in Ri is equal to 1, and for all y not belonging to Ri, I have pi I of y is identically 0. And of course, based on the first result applying to the set Ri, then that pi I has to be unique inside Ri. So, well, the remark can be long, but then let me discuss the practice to see, to illustrate the idea of this. So, practice number 1, problem 2. Okay. That should be on CLA as well. So this is CLA. So given this centration matrix, first thing I'm going to do is to draw the diagram. It's actually something I already did before. From 1, say 1 here, 5 there, 2, 3, 4, 6, and 7. And 1 go back to itself. Go to 5 and 5. Go back and build up to 1 to go like this, and 2 go like this. 4 can go to 6. 6 go back here. 7, 7 back 4. All right. So you can see immediately that S can be decomposed as the first set of the transient state 3, right? 2 and 3 being transient, a union with the first closed irreducible set, which is 4 and 5, union with 4, 6, and 7. Alright, so here, this is my T. This is a R1 here, and this is a R2. Yeah. And so the remark basically saying, I'm gonna have a stationary distribution concentrated in 1 and 5. And similarly, I'm gonna have another stationary distribution concentrated in 4, 6, and 7. So I have two distinct stationary distribution on the whole state space S. Alright. And here that will give me a pi 1, and over here that will give me another pi 2. Alright. And in order to find pi 1, all you have to do is just to concentrate onto 1 and 5. So if you forget everything, right? So say to find pi 1 on R1, right? 1 and 5. So you only need to consider the state space 1, 5, and 1, 5 only. Because if you rearrange the matrix, you will see that 1 was 1. So 1, this is 0.7, 0.3, this is 0.6, and 0.4, right? And so given the omega, that would be like a 0, 0 here. 0, 0, 0, 0, 0, 0, 0. Right? So whatever you how you get. Right? If you rearrange the matrix, that's what you will see. In other words, 1 and 5 could be considered as a state space for a Markov chain with this 2x2 transition matrix. If I'm starting in R1, I'm going to stay there forever. So now if you want to solve for pi 1, it should be good. Right. So now, solving for pi 1 should be, and then we solve for pi 1, right? Yeah. And so, and then we have what? So I have pi 1 multiplied by the matrix 0.7, 0.3, 0.6, 0.4 is equal to pi 1. Alright. It shouldn't be difficult there. Similarly, concerning the 4, 6, and 7, you will be able to find pi 2. So if I rewrite the matrix, I rearrange the matrix like 4, 6, 7, 4, 6, and 7, right? What is 4, 6, 7? 1, 5, 0. 6 will be 0.2, 8, 0, and 7 1 here, 0, 0. So the rest here is 0. And this is 1 out, right? And so 4, 6, 7 can be considered as a state space for a Markov chain associated with this 3x3 matrix. Right, so 4, 6, 7 is a state space itself, right, for the 3x3 transition matrix. you can solve for pi 2 easily. So then pi 2 is just that. Pi 2 multiplied by the matrix 1. 0, 0, 1, 2, 1, 8, and 1, 0, 0. You see, pi 2. Yeah. Of course, this pi 2 here has three entries, 4, 6, and 7. So, all right. So, but anyway, I guess it shouldn't be difficult here. So how about 2 and 3 transient? How about transient states? There will be no stationary distribution on the transient space. In other words, if I have pi being a stationary distribution, then pi 2 gotta be 0, pi 3 gotta be 0. So that was a result that I mentioned the other day, I believe. So we don't have to worry about the transient space here. All right, so I hope that this is clear concerning the stationary distribution on each of the closed sets. All right. So now let me walk through each of the limiting. All right. So the first one is the limit of Pnx2. Yes, I need to recall that lemma. This is lemma 6, right? So this is, I remember when lemma number 1 is f y transient. Then Pn xy will have to converge to 0 for all x. So, given that lemma number 1, I can say immediately that because 2, well, 8 years, let me rewrite this. 2 and 3, union with I shouldn't have erased this. 6, 7. This is the transient. This is R1. This is R2. I have a I1 on R1. I have a I2 concentrating in R2. All right. Let me move over here. So now because 2 is transient, right? For every x, Pnx 2 has to go to 0 immediately. So since 2 transient, right? For every x inside state space, Pnx2 has to go to 0 immediately. Yeah. Based on that result up there. So now, okay, next one. Pn14. What can you say about Pn14? Zero, right? Because 4A belongs to another closed set, so they don't communicate at all. So that is clear. That is actually ethically 0, which obviously go into 0. PN 15. So PN 15. How about this? Yeah,
You get that from the stationary distribution?
why is that? So which results can I employ here? I need to have irreducible,
Yeah.
that's clear, right? Second, the result.
Yeah.
I need, R1 is irreducible, so in R1, 1 and 5, right? So R1 is irreducible for sure. Does R1 have a stationary distribution?
Yeah.
Yes, pi 1, right? So I guess I wanna call maybe R1, so, pi. What is the notation here, maybe, kinda clumsy here, meaning, this, I guess, so let me write the word here, so, pi 1 is the stationary distribution, in R1, right? What am I missing now? The last piece, a periodic. Is that true for R1? Yes, right? So R1 is, it is clear that every state in R1 here, 1 and 5, they have to, all the periods here, are, so I have, plus A, right? As a consequence, this will converge as n goes into infinity to I1 evaluated at 5. Yeah. So, similarly, how about PN 47? Similarly, PN 47, but the concentrating focusing now in R2, 4, 6, and 7. So R2 is closed, irreducible. I know R2 has a stationary distribution, and R2 is also aperiodic because 4 has period 1, triple and the same for 6. And for 7, that's because they all communicate with one another. All the periods have to be the same based on that lambda number 6. If they communicate, then they need to have the same period. Right? And so in order to determine the aperiodicity, you only need to find one state with period 1. And then the rest, every other state inside the closed set, other irreducible set, we need to have the same period 1. Yeah, so it's only need to, but here, I mean, in this particular picture, it's pretty clear now. So I have R2, right? So in R2, I have irreducibility plus I have a stationary distribution pi 2, and R2 is a periodic, and go into infinity. Pi 2. So, yeah. Good. So, I guess let me mark here concerning the period. So if it says C is irreducible, and there exists, say, and say for one element X, in C, that's so we want to say concerning period, C is irreducible, and suppose X in C has period. That's period, let's say D, alright? Then all the element, then all for Z in C, period of Z has to be the same. Right? Okay, so if I know one state, B having the period 1, then my irreducibility, any other state inside of that set C will have the same period. Yeah? Okay, so the proof shouldn't be difficult, just consequence of the lemma number 6 above. Alright. So, last piece. How about Pn2? It should be 0. Not really. It's actually not 0. Not 0. No. So which result can I employ? No result at all. So we just go for it. You already passed. Right? Then you could say, okay, so the question has how many? 1, 2, 3, 4, 5. So 5 questions, 5 limits. Work out 4. You just submit it over. You already passed. If you want a good grade, you need to follow the theorem concerning the transient and the recurrent. So the next one is, what was my labeling? So that was the lemma 6. Anyone, I forgot to keep track of the numbers. I guess that was 9. That table was 9.
Lemma 7.
That was number 7.
That was lemma 6.
That was number 6, I believe.
Yeah.
So that was the,
Yeah, that's the last one.
that's the last one.
Yeah.
So I guess that table will be theorem 7 maybe?
Yeah.
Maybe.
Sure.
Was there any definition in between? No? No
No.
definition 7 something?
No.
No. Alright. So if that was theorem 8, then, oh, sorry, 6, 7, so that would be 8. Alright, so suppose C is a closed set of, a closed set, closed, irreducible, closed irreducible set. Alright. And suppose Y in C is what? Is, well, I mean, this one guy is recurrent, and every guy has to be recurrent. So I guess if it's closed, irreducible, of recurrent. Okay. So if one guy is period one and the other one, alright, so my bad is my bad, so let me write it. Suppose C is a closed set, right? C is a closed set with following irreducibility plus recurrent plus a periodicity, right? So C itself is a closed set of irreducibility, recurrent, and a periodic. Then for all x in the whole state space and the y in C, Pn xy will converge to, and go into infinity, the probability starting from x to C be infinite, multiply with pi C in okay, so I guess I need this as well, so where T sub C is just the first time I hit, I enter set C. So n greater than 1, what is this? N greater than 1, x, and belongs to C, right? And pi sub C is the stationary distribution on C. So I guess over here, I need to have plus pi C, okay? Of course, I guess I will say, but actually this is 0, because I want to count all the cases. So actually this is kind of like a generalized version of the second result I wrote there. Alright. So this is actually pretty intuitive. Suppose I start from 2, right? In the long run, I would have to enter R1 at some time. Here. And then starting from there, because this set is already a periodic, and so from that location it will convert to 1, and the limit is the power here, evaluate at 1. Alright. In particular, that does imply the limit does exist. Alright. And the value is, even though you may not be able to compute this, even though, but we know for sure the limit has to exist. Right. And so then this one, should I erase that? Maybe move it up. Maybe move it up. So, all right. So to see that this is actually a generalized version of the second line above. So if I employ this theorem, right? And you go back here. So you go back. So you see it's Pn. What was the Pn 1,4? Let me go back to illustrate. Right. So Pn 1,4, according to the result, will convert to probability starting from 1. I will hit the set R2 in finite time, multiply with P2 4. Right? What is that probability? That is 0. Right? Obviously, because if I start from 1, I can never hit the set R2 in finite time. This is 0, right? So the limit is 0, consistent with what we already have. Similarly, say Pn15, this will convert to 1 Tr1 infinite time I15. Yeah. However, if this one is already inside of the R1, and remember this Tc here, starting from counting time 0. Alright? I'm counting starting from time 0. So if I start at 1, I'm already inside of R1. And so this probability is trivially 0. That's not bad. 1. Yeah? Trivially 1. Right? Because indeed, if I start from 1, the Tr1 in this case is identically 0, which obviously is finite. Yeah? So the limit will be pi15, corresponding to the second line, second result. Yeah? So now the last piece is Pn what? I forgot. Pn21, right? So now the last piece is Pn21. So now Pn21 will convert to probability starting from 2, hitting R1 infinite time, multiplied by pi1 evaluation. Alright. Now how do I evaluate that? So it actually just, so now, in particular, this must imply limit of Pn21 exists. So, how do we evaluate it? So you just solve this. So Pn plus 1, 2, 1. Alright. You do it's called a one-step analysis. In order to get from 2 to 1 in this number of steps, I need to go to Pn, where I could go at the step, and I have to land at substitute here beside. I guess I can go with this. P21, Pn11. Yeah. In step 1, I have to hit either 1, and then from there going to 1 n steps. P22, Pn21, plus P23, Pn31, plus P24, Pn41. Right? They are the possible paths that I could go in one step, starting from 2. On possible path. In one step, so from 2, I can only go to 1, 2, 3, and 4. Right. So if I take the limit, right? Suppose let me denote the limit of this to. So I guess let me denote. Say C21, say, meaning the limit of Pn21 as n goes to infinity. Alright. So if I take n to infinity, this will go to C21. This is already clear. This will go to pi1 of 1. So I guess let me write it down. Right over here. So now take and beginning, the left-hand side will go to C21, right? Now the right-hand side, I have P21 is a constant. Pn11 will convert to pi1. Yeah. And then I have P22. I have C21 again. Right. And then plus P23. Now multiply with C31. The limit of Pn31. Alright. And plus P24 times, well, that's 0, right? This is identically 0. So I guess I don't have the last row. Yeah. So I guess over here in the notes there's ABC, X, and Y. So forward, and then we can. Okay. Okay. So here, well, I should have mentioned that Pn31 will convert to C31, a number to be determined. But I know the limit has to exist. That's what I know for sure. All right. I don't know the value for the moment, but I know Pn31, this guy right here, it has to convert to a limit denoted by C31 to be determined. All right. So that is, so basically I have a equation on C21 and C31, two unknowns. So how do I get out of this? How do I know this, right? So now you have to start with the P and 31 as well. So you have Pn plus 1, 31 is, do the same thing. In order to go from 3 to 1 in this number of steps, first step we have to go P35 multiply with Pn51 plus P3, where does it go? You can only go to 4, right? Am I correct? 3 going to 5, 3 going to 4. That's it. P and 4. 1. Right? So in one step, I can only from 3, I can only go to 5 or 4. But this guy is already identically 0. Right? And so taking the limit. So taking the limit, this going to C31 equals to P35. Pn51 will convert to pi11. Yeah. This is because this here convert to pi11. Yeah. So now you can solve for C31. You can solve for this number and plug back in here. So for C2. Okay. Question?